Today I want to tell you about how to use on-chain randomness on Aptos. So let's go over an overview of this talk. First we're going to talk about why are we providing on-chain randomness on Aptos. Then we're going to present our randomness API, but we're not going to discuss how this API is implemented. We're just going to discuss what it does. And then I'll show you an example of a Raffle dApp, and then I will show you how to write these randomized dApps securely using our API. So let's begin with the why. Why provide randomness? I think the main reason is that it opens up a lot of new applications. So things like games, raffles, lotteries, randomized NFTs, randomized airdrops, interactive zero-knowledge proof verifiers on-chain. And in general, you are here to tell us what kind of other applications this will open up. So we're very curious to see what you come up with. And in particular, why provide on-chain randomness? So as some of you know, you might have used external randomness beacons, and these are great, but they do have some disadvantages. They are easy to misuse. So for example, you have to deal with round numbers in your code. In contrast, on-chain APIs can be very safe, very easy to use by default and safe by default. They're too pricey. On-chain APIs are very cheap. You pay a small gas fee to use them. They're too slow. 1 value per second, for example, if you use the DRAND randomness beacon. Whereas an on-chain API is very fast. You can produce randomness as quickly as you need it by calling a move function. And they require additional transactions to ship this randomness to your contract. Whereas with an on-chain API, you can directly return the randomness to the caller. And lastly, they have potentially weaker security, whereas an on-chain API is as secure as the Aptos blockchain itself. Good, so now that we know a little bit about the why, let's see how the randomness API looks like. And there will be a randomness move module, which is going to look like this. There will be various functions that will allow you to fetch random objects. So for example, you can call this bytes function, which takes a certain number of bytes and outputs to you a vector of random bytes. Or you could call a U64 integer function, which returns a random U64 integer, or a U256 integer. Or maybe you want a U64 in a particular range between A and B, or a U256 between A and B. You can even generate a random permutation of a vector. And we're thinking of adding other functions as well, but for now, we'll start with a simple subset like this, which will allow you to do pretty much everything you can imagine. And lastly, for your test, we're going to have a test-only function called setSeed, which will allow you to set the entropy in the random number generator so that you can generate predictable numbers in your test cases. And an important thing to understand about this API is that repeated calls to the same functions in your contracts will resample a new random outcome. So for example, if I call U64 integer for the first time, maybe it's going to give me a number, say 13. If I call it a second time, it's going to resample, and it's going to give me a fresh random number. It could be 13, it could also be 14, 15, 27, whatever. It's a new sampling. So every time you call a function, this samples a new number. And I think this is the main thing you want to understand about this randomness API. Every time you call a function, there's a new sampling happening, and this will have some consequences, which I'll discuss later in terms of security. So now that we know what the API looks like, let's see how you can use it to develop a Raffle randomized dApp, or a randapp, like we like to call it. So let's begin by showing you a Raffle resource. So this resource keeps track of the people who bought a Raffle ticket and their address. And it keeps track of the total amount of coins that have been deposited into the raffle when the tickets were purchased, and of a Boolean that indicates whether the raffle has finished or not. To buy a ticket, there is a public entry function called buyTicket, which takes a signer. We try and access this Raffle resource, and then we charge the price for the ticket, and then we move this whatever was charged into the Raffle jackpot. And then we are ready to issue a ticket for a user. In the ticket vector inside the Raffle resource, we push the user's address, and then we're done. The ticket has been bought. To pick the winner, we're going to have an entry function called randomly pick winner. This will also acquire the Raffle resource. First, it'll check that the raffle hasn't been closed. Then it'll check that there are people who bought tickets. And then it'll be ready to pick a random winner using the randomness API I just showed you. So here, for example, we're just going to pick a random number between 0 and the number of people who bought tickets. This will make sure that we're picking a random winner. And now we're ready to access this random winner in the Raffle ticket vector and get its address, and then we can pay the winner. So we can extract the Raffle coins and deposit them in the winner's account. And then we can close the raffle, and we're done. So as you can see, it's very simple. You just call a U64 range function, you get a random winner, you extract the coins, you pay the winner. But of course, things can be a little bit subtle in practice. So let's talk a little bit about how to write randapps safely. So there's a class of attack associated with randapps called test and abort attacks. So in these attacks, what you can do is you can wrap this public function that I just showed you, this random winner, randomly pick winner function, and test the outcome. And then if you don't like the outcome, you can abort it. So here's how this attack would work. So what the attacker would do is you write a move script where he fetches his own address, and then he fetches his balance before calling randomly pick winner and after calling randomly pick winner. And he can check if his new balance is the same as his old balance. If that's the case, that means that he didn't win the raffle because his balance hasn't changed. So then he can abort the transaction. So that's not so great because the attacker can repeatedly do this until the new balance is changed and until he gets paid, and actually bias the choice of the winner in the raffle. So how do we fix this? A very simple fix for this is to change the public entry modifier of the randomly pick winner function into a private entry function modifier. And this ensures that this kind of wrapping that I showed you here cannot happen in move by moving it from public entry to private entry. It's a very trivial fix, and in fact, you don't even have to worry about this attack in your random contracts because the APIs, the U64 range API, will check the call stack and ensure that it's being called from an entry function. So this is something that we plan to proactively defend against so that developers cannot make this mistake. But I wanted to showcase this attack anyway to illustrate some of the difficulties associated with randomness inside smart contracts. Now, there's an even more interesting attack possible. So in some randomized apps, execution time could vary based on the sampled randomness. So to give you an example, imagine you have a game and you toss a coin. This coin toss will create maybe 2 execution paths in this game. So if the coin is a head, then the player might get 100 coins as a reward if he tossed a head. And if he tossed tails, then the player maybe loses 10 coins and loses 10 health points and 10 armor points. And you can see that this execution path will have lower gas cost than this execution path, because this execution path is doing 3 different things, whereas this guy is just doing 1 thing. So what an attacker can do is he can actually undergas his transaction, so he can supply it with less gas to ensure that the high gas path never finishes executing and the transaction aborts. And this will always guarantee that the attacker's transaction, if accepted, will get accepted under the lower gas path execution. So the attacker can basically ensure that this outcome, which is very positive, happens all the time. So let's look at an example. Imagine you have a game that does some coin tossing at some point. So there might be an entry function called coin toss, which takes the player's signer as input. And you might just simply fetch a player object using the signer and check that the player hasn't tossed a coin already. And if he hasn't, you toss a coin for the player. We simulate this by picking a random number between 0 and 2, where 2 is exclusive. And you check, is the random coin 0? In other words, is it heads? If it's heads, then give player 100 coins. This is the low gas path. And if it's tails, then punish the player. This is the high gas path. So the player will lose 20 coins, it'll lose 10 health points and 5 armor points, let's say. And lastly, mark that the player has tossed a coin so that he cannot repeat this multiple times. And this seems like a relatively harmless piece of code that you could write, but it actually has an attack in it. The attack that I just mentioned before, where the execution gas depends on this random variable, random coin. So this path has lower gas than this path. And the way an attacker could leverage this, as mentioned before, is by undergassing his transaction. So to fix this type of stuff, what you want to do is first commit to your coin toss, commit to your random variable that you pick. So we're going to split this earlier function into two functions. The first one is coin toss commit. It does the same thing as before, except after it picks the random coin, it stores it in the player resource as committing to it if you want. And then there's a second function that actually applies this outcome from the coin that was committed to in the resource. So in this function, you fetch the player once again, and you check that he has tossed the coin indeed, and then you access that coin and you deliver the outcome. And now it no longer matters that this is a low gas path or a high gas path because the random variable has been committed in a previous transaction. And that's basically the fix, and that kind of ends the tutorial. I hope you guys enjoy hacking, and happy to take your questions on how to use this API safely. Thank you.